Hi, let's walk through how to create a multivariable linear regression model. In this example, we will explore antelope data. Before building the model, let's look at this example code, where we will first check to see if there's a linear relationship between the data. We do this by checking if there's a line in the data when plotted, and also the correlation between each independent variable. Let's run the code to check. In the console, we see the correlation values. The correlation between annual precipitation and fall population is 0.92. This indicates the annual precipitation and fall count have a positive linear relationship. The second line shows the correlation between winter severity and fawn population. We see that it has a negative linear relationship. We can see in the scatter plots a line in the data. The top has a positive line because it has a positive linear relationship, and the bottom has a negative linear line because it has a negative linear relationship. Now that we've determined that there is a linear relationship with this data set, let's build a multivariable linear model. I went ahead and imported pandas and the sklearn modules we'll need to build this model. First, we need to read in data from the CSV file. Next, we extract the x and y values from the dataset. When there is more than one variable, you pass a 2D array with the strings of the name of each column between the square brackets. Next, we separate the data into training and testing data. Now it's time to build our model, and we fit it using the training data. Great! So now that we have our model, we can extract important information from the model. Each independent variable has its own coefficient. For the first independent variable, annual precipitation, we can access it by writing model.coef underscore and then in square brackets 0, because this is storing an array with more than one coefficient. We can also round this value by 3 decimal points. For the coefficient for the second variable, the winter severity, we do the same thing, but instead, we access the value at index 1. For the intercept, or bias, we use intercept underscore. Let's also round this value by 3 decimal points. And for the r-squared value, you can use the score method and pass the training data as arguments. Let's run the results to see what's printed in the console. As you can see, annual precipitation has a coefficient of 0.795 and winter severity has a coefficient of 0.466. So this means that the model should give more weight to the annual precipitation when it's predicting values for fawn count. Now let's explore how well the model is at predicting these values. Like the previous examples, we will print the x value, the predicted y value, and the actual y value to compare the results. Now let's rerun the code to see how well it performs. As we can see here, the annual precipitation was 10.6, the winter severity was 5, the predicted spring fawn count was 2.44, the actual was 1.9. For the second example was 11.2, with the winter severity of 3, the predicted spring fawn count was 1.957, and the actual was 2.1. Great! Now it's your turn to explore this example.